I'll quickly make sure we're live. I always get worried if I'm missing something and sometimes it doesn't go through. So just give me 10 seconds.
Sure, sure.
Awesome. I believe we're live on YouTube. So I'll quickly introduce today's guest. Hey, everybody. Thanks for coming back to the JAX Talk series. This is co hosted with Christian, who'll join us in a few minutes, I believe. Christian is the real host who brings in great guests like Eugene, who's a research software engineer at Google Brain Japan, which is why we have the chance to host this during day this time. Sometimes it's in the evening for me. So that's why I see the daylight. Christian is here. Hey, Christian, I'm just introducing Eugene.
Hey everyone.
Hi, Christian.
So I was just mentioning about EvoJAX, and for the audience, Eugene will be talking about EvoJAX, which is a hardware-accelerated neuroevolution framework built on top of JAX. We've been hosting a series about a bunch of RL libraries recently, and this is somewhat similar to that. Eugene also has some interesting examples to show us, some live demos, so I'm always excited about that. With that, I'll hand it over to Eugene. And before that, Christian, do you have any other comments for the audience?
For now, no. I'm super excited about this topic. It's one of the interesting cases where it's okay. Let's see something new.
Awesome. Over to you, Eugene.
Okay, cool. Yeah, thanks for having me here. So hi, again, I'm Eugene. I'm a research software engineer at the Google Brain Tokyo team. So what I'm going to talk about is a software toolkit. It's called EvoJAX. It's a hardware accelerated neuroevolution toolkit. So this is a joint work with my colleagues Intel 10 and David Ha. So let me give you a brief description. So first of all, you may wonder like, hey, what is EvoJAX, right? Apparently, it got two words there, Evo and JAX, right? So if I have to summarize EvoJAX with like a really simple sentences, then EvoJAX is a neuroevolution toolkit that's accelerated by hardware accelerators. First, I'll just talk about like what's neuroevolution. Like neuroevolution is uses evolutionary algorithms to say, for example, generate artificial neural networks and also train their weights to solve problems. And one feature that I want to highlight is that unlike backpropagation, neuroevolution does not rely on the differentiability of the entire system. So that means with neuroevolution and the genetic algorithm or evolution strategies it included, it could solve problems that involving non-differentiable systems. I will talk about examples of non-differential systems later. But this is just one feature of evolution. Another feature is that so evolution, the second keyword is JAX, right? So we built this entire software using JAX, the currently popular ML framework. And because of that, our toolkit is hardware accelerated. It runs on CPU, GPU, and TPU. And most importantly, it does not require any complex settings. So you could run all this code within one box as long as it has sufficient hardware support there. I gave several like examples at the bottom of this page. For example, these are kind of like the first two are kind of like the popular tasks there. The first one is like a robotic locomotion controller learned in a physics simulation environment. In this case, we used the BRAX. I guess the audiences here are familiar with BRAX, right? That's also something developed by Google recently. And the second example is the classic cart pole swing up task. Like for these two tasks, previously using a conventional, say, framework like evolution framework from Google Brain, when we compared it, we find that these tasks could reach a 10 times or 20 times speed up if we train these tasks with Neuroevolution with AppleJAX. So that's kind of the steep speed up we could get. And the other two tasks I want to introduce is that you see the third picture. It's called like a water world. The original author is like Andreas Karpathy. He used like JavaScript to develop this interesting environment where the agent has an array of sensors and it's supposed to catch food as much as possible while avoiding these poisons. So the agent has a certain dynamics, and the algorithm has to learn to control the agent such that the agent could steer clearly out of the way to get as much food as possible. And the last example shown here is from Intel, our colleague. Where in this example, he showed that it's possible to do some abstract painting with only triangles. In this example, actually, there are only 50 triangles. And the agent is supposed to arrange these triangles such that the position as well as the color could match a certain given image. In this example, Mona Lisa. Yeah, so I would just want to highlight that with EvoJAX, we can do all this kind of stuff and with great speed up. So, okay, so I guess you get a rough idea of what EvoJAX is. Then the next question is why we made EvoJAX. So why EvoJAX, right? So we majorly got two things in mind when we designed EvoJAX. So the first thing is that we want to broaden the range of tasks and problems that Neuroevolution, or say we could solve. Currently, deep learning works great, right? We have this deep learning for supervised tasks and also deep reinforcement learning for some reinforcement like robotic control tasks. But the thing with that is that they are all trained rely majorly on backpropagation, which requires the network or the systems to be differentiable. But there are a lot of problems in real world that does not guarantee us of this differentiability. The example that I can give you is, for example, I put a robotic example here, right? So in robotic tasks, there are a lot of discontinuities induced, for example, by collision between these rigid bodies. Say if you want to learn the physics of a simulator system, what we usually do is to create a neural network, usually of continuous operations, and we then collect as much sample as possible to try to fit its neural network to say imitate the physical behaviors of the real environment. But usually this kind of discontinuous behaviors is hard to learn for a neural network full of continuous operations. So we are thinking of, say, maybe we could compose a network, a network model that contains also discontinuous operations, and then use that model to fit the entire physical dynamics. Maybe that will make the problem easier. So that's one way we could broaden the range of the tasks. Another thing is not on the task side, but on the solution side. Say, for example, in the evolution researches, we have this spiking neural networks where the operations are discrete and not differentiable, not easily trainable with deep learning methods. Although there are strategies that try to, say, develop some surrogate losses or, say, surrogate functions, try to bridge this gap so that spiking neural network can also be trained with deep learning. But I think that's kind of a non-trivial, and it requires some creativity in designing such tricks. And also, what I show here, in the middle, is another work that we released, I think, 2 years ago, where the network contains also some discrete functions. In these examples, we asked the agent to segment this input image into patches. And then the patches will vote to each other, say, who's the most important patches among all of them, right? Then the agent will select only the top K, in this example 10, the top K patches out of the entire image, and then make decisions based solely on the information provided by these 10 images. So that's why you see there are white patches. So these white patches are where the agent decides where it should focus its attention on. Like in the car racing example above, you can see that almost all the white patches are on the road boundaries. So apparently this agent figures out that to drive in a car, you need to watch out where the road is. And in the second example, in the bottom row, the agent tries to dodge the fireballs from the enemies, and apparently focuses majorly on the enemies as well as the fireballs. So for this solution network, we have the sorting of the patches as well as the truncating of these patches. Both of them are like a discontinuous operations, which is not easily trainable with backpropagation. And that's why in that paper, we trained with the CMES, a neuroevolution algorithm. So with that said, what I try to say is that with neuroevolutions, we could potentially broaden our the task range and the solution range that we can explore and try and solve in the future. And the second reason is that so neuroevolution has been for a while. However, like most of the conventional, like for genetic algorithm, for example, the conventional implementations usually will spawn a population of potential solutions together with the tasks. Each solution is evaluated in a separate thread or maybe process, which will utilize, say, a different CPU, for example. And then in each iteration, these individuals will, after evaluation, their fitness scores, or say utility scores, will be collected and evaluated back by the neuroevolution algorithm, which will then try to get to who is the fittest, right? Try to make those the ancestor of the next generation, and this iteration goes on and on. So that's basically how neuroevolution of the genetic algorithm works. So this process is okay, but in the conventional computational frameworks, this majorly relies on CPUs, and apparently they mostly run on a cluster of machines. So this brought like two problems. First, maintaining a cluster for machine or setting up a cluster for machine is non-trivial. So this kind of engineering task is not desired by everyone, right? And the second thing is that if you try to implement this framework with, say, modern ML frameworks, say TensorFlow or PyTorch, because these frameworks were originally designed for deep learning tasks, and they didn't have this like distributed computation in mind in terms of evolution computations. So the implementation is going to be tricky, and we often run into difficulties implementing such systems. Plus, this will require you to, say, maintain in each process a separate policy. In this way, essentially, each process is going to create an identical computational graph for the same policy, which is not very efficient way of using resources. So with these two major difficulties, we present EvoJAX here. So as I said previously, EvoJAX is built on top of JAX, another recently popular ML framework. So with JAX, we changed, we implemented the three major components of neuroevolution: the neuroevolution algorithm, the policy, and the task, all in JAX, and we compile it just in time. And we fully utilize JAX's the auto vectorization mechanism provided by JAX. So by doing so, the benefit we get is that so first on the algorithm side, from JAX and other like examples, we got this advanced optimization functionalities. For example, we could use Adam or some other deep learning tailored optimization tricks, all from this toolbox. So this gives us access to this matured machine learning like a tools. So that's one major benefit we get. And the second thing is that with auto vectorization provided by JAX, we no longer need to create a separate process for each evaluation process. Instead, we could only create a global policy network in JAX, and then during evaluation, instead we provide two batches of data. One is the parameters, that's the potential solutions. The other is the observations. So they are treated as batch data, just like in supervised fashions. And then the network will spit out the different actions for different policies. And then these output will be inputted to the third component, which is the vectorized task, also implemented in JAX. In this way, we observe like high data throughput on through the entire data pipeline, and usually a task takes only like minutes or tens of minutes to train instead of days or maybe weeks in the conventional framework. Okay, so I think that's all I want to cover about EvoJAX, the motivation about EvoJAX. Next, I want to present some of the demos, like what EvoJAX could do. Just give me a sec.
In the meantime, I'm not sure, Christian, if you have any comments. I had a silly question. Please correct me. Please stop me if this is too stupid. You mentioned traditional frameworks weren't built for distributed training. So when we talk about PyTorch distributed or TensorFlow has similar extensions, how are they not sufficient? Could you please clarify?
Yeah. So the way we see it, that I specifically said that they are not say they do not support distributed computation in the context of evolution strategies. So what I mean is that with supervised learning, you could distribute your data or your policy network. Maybe part of the data is spread out on multiple devices, and maybe this policy network is partially resides on different devices. So that they can do. What I mean is that for each, say, evaluation process, you need to, for that this is specific in this genetic algorithm or say neuroevolution's context, we need to create a like a computational graphs for the same policy on each processes. For this way, usually, for PyTorch, for example, it will complain, say you cannot say create on the same devices the exact policies cannot spawn it twice. So it's kind of become tricky. You have to say if you are going to spawn this process using like the multi-threading system, you have to use fork instead of sprung. So it's doable, but it's non-trivial. So there
Makes
are,
sense.
yeah. So there is a layer of difficulty on top of it, which is not say easy for us like neuroevolution practitioners.
I have a related question.
Sure, sure.
Um, because we had one of the authors of Brax here.
Yeah,
So it was okay. This is really cool. Like you can run basically here would be kind of the environment on also on, let's say, a TPU, which I mean
yeah,
it's a bit crazy.
yeah.
uh, but some of the examples, I don't know if they are kind of more traditional or what I wanted to ask is does it require the environment itself to also be compiled through JAX, or is it like you can just use whatever?
I see, I see. Yeah, that's a great question. So right now, for the current release, we require the task to be also implemented in JAX. So that is from a performance perspective. So when we developed the EvoJAX, we tried to integrate the traditional tasks as well. But most of the traditional tasks, say PyBullet, for example, it runs on CPUs, right? So although the policy and the optimization itself are run on GPU, but this data transportation between CPU and the GPU is going to kill the extra benefit. So that's why we recommend for currently all the tasks to be implemented in JAX. With that being said, there are other tasks, say Isaac Gym, which is released by NVIDIA, right? So although it's not in JAX, it's currently implemented major in. I mean, it currently supports PyTorch users. So in the next release, EvoJAX could also integrate with Isaac Gym, which is not in JAX but in PyTorch. So we could train this kind of hardware accelerated environment as well, but not in the current release. Just to be clear.
Hmm. And for environments that are not in JAX, like currently the strategy is kind of to run them on the host and send the data, something like that.
Sorry, can you say it again?
So for example, for environments that are not in JAX, which I guess that means they're not easily distributable to the
Yeah.
cluster, like they would run like on the host machine. I don't know, like uh, the host environment, and then you send like the data to the cluster, and that's kind of how it would work. Or currently you require also the environment to be able to
Yeah, that
somehow distribute itself.
Yeah, I see, I see, I see. That's a good question. So what comes with EvoJAX is that although I said that there are three major components provided by EvoJAX: the algorithm, the policy, and the task, right? But beyond that, we also provide a super fast training loop to orchestrate to maintain the entire training process that's
Hmm.
transparent to the users. And due to this efficiency, we want to get this efficiency. So this training loop utilizes a function that's in JAX. It's called a scan. So we utilize that one to make this training loop really fast. Unfortunately, this function scan does not support other like environments that's not implemented in JAX, or say in NumPy friendly way. So there is no way to incorporate the other relatively complex tasks.
Mm,
But if the task is simple, like in NumPy, I guess that's okay. But if, for example, maybe Pyball is other stuff, maybe we have some difficulties here right now.
mm, interesting. So for example, the car environment you showed in the pictures, you ported it to JAX?
No. So that one is used here to illustrate the potential solutions that we could try with EvoJAX. And for that one, the simulation environment is written in Box 2D. So
Mm,
I see some people are trying to migrate Box 2D to either NumPy or JAX. I don't know whether this has happened in the short term, but that's not what we have in the JAX EvoJAX repository right now.
okay. Okay, I see. So the requirement is everything in JAX.
Yeah, in the current release, right. But as I said, this is for a reason, because we want to make everything fast, right? Making part of it run on CPU, and the data transport between CPU and GPU will kill the entire benefit from accelerator. So I guess that's the reason.
Mm. I, I have another question. I don't know if this is too deep, but I
Yeah,
was kind of looking at the code. I saw some examples where you were using Vmap,
yeah.
but you're kind of also using something like Pmap, like using like
Right.
the TPU cluster. I don't know. This is true, or you try to run them on CPU?
Uh, so using Vmap and Pmap, so using Vmap is majorly to a way to make to make environments easy. I mean the task easy. So as I said, for AppleJAX, we created these vectorized environments, right? But we don't want users to keeping conscious to say this environment is going to be vectorized. So I have to always remember there's going to be a batch dimension. So we don't want users to keep that in mind. So that's why we use Vmap mostly in the task creations. In that way, for example, the cart poll could be composed as if it's just a single environment, right? And then later on, we just wrap it with Vmap, then it automatically become a vectorized environment. So that's why we use the Vmap. For Pmap, we just want to distribute when you have multiple TPUs or GPUs, you want to distribute both the policy network as well as the tasks to multiple devices. So that's why we use this Pmap, mostly to distribute this workload to multiple accelerators. Yeah, that's kind of the reason of using Vmap and Pmap here.
That's really cool. So the card poll is implemented in JAX right now. Like,
Right. It's implementing Jackson, but yeah, it's kind of easy. So we provided I'll show that as well later. So we provided a tutorial for how to create tasks, policies, and the Neuroevolution algorithm all in JAX. So we have defined several interfaces. As long as these interfaces are implemented, the user extensions could be run seamlessly within EvoJAX.
mm, yeah, it's really cool. So I don't know, because most people out there are probably thinking of like something like OpenAI Gym,
Yeah.
uh, and I guess that uses sometimes like Box 2D. I don't know, like so you're kind of dependent on this idea of, okay, let's implement Box 2D in JAX also.
Yeah,
Like,
yeah. What I'm saying that is that yes, I admit there will be some limitations here. Like for Box 2D stuff, probably it's not easy to run it right now. At least not in the current release, because we only support JAX-based environments. But it will be possible in the future, as I said. But again, although it's possible to run that, but the performance may not be that great, because as I said, you are going to facing this data transportation between CPUs and the GPUs. So
mm,
so so yeah, that's kind of the trade-off you have to pay there.
okay, interesting.
Yeah, we expect, say, like especially the researchers from neuroevolution societies to put their implementations of novel tasks within the framework of EvoJAX. In that way, they could quickly try their ideas and get some feedback, in like minutes or hours instead of days and weeks. Yeah, you'll see some interesting examples later in this talk.
Sorry, I'll ask one question from the audience. Have you seen EvoJAX, and what is the difference between these two?
Yeah. If you go to our GitHub front page, you could see that EvoJAX is a sister project of EvoJAX. Actually, Robert, the author of EvoJAX, has contributed quite a few PRs to EvoJAX. So the major difference is that we focus on different parts. EvoJAX has a wider range of neuroevolution algorithms implemented, whereas EvoJAX focus on the entire pipeline. So we have this algorithm, but at the same time, we focus on the easy integration of new tasks as well as novel policies. So that's the focus is different. I would say this is the major differences there. But as I said, if you go to our page, you will see some EvoJAX implementations already in EvoJAX, and it's runnable there.
Thanks for answering that.
Yeah. Okay. Do you mind if I proceed to demos?
Sorry for asking so many questions, please.
Yeah, no problem. Okay, I will present you two demos in this one in this talk. So if you go to our GitHub, there is a example directory under which we have a lot of like notebooks that are readily runnable. I'm going to show. Yeah, I guess you've already seen these Brax tasks before. Yeah. So I won't run the examples here because I saw the presentation by Daniel last time. He already presented the similar examples. So what I want to demonstrate is that this notebook is mostly based on their notebook. So a lot of like task creations code, we are using the same part. What's different is that the training part. So in this example, for example, we are training local motion controller for this ant robot, right? So the difference is that this is the part that we replace the training code with the EvoJAX. What I want to highlight is that, so first let's look at the training time. EvoJAX is able to train the ant task to a decent score. Actually, this score is higher than what they show in the Brax demo within, like, I think it's within 10 minutes, something like that. And what I want to highlight the other is that, so this is the training loop we provide here. As I mentioned previously, so in addition to the three major components provided by EvoJAX, we also provide a trainer and a simulation manager that orchestrates the entire training loop. And what I'm demonstrating here is the logic of this trainer stuff. So as you can see here, the code is relatively short, and the logic, I think, is quite simple. For users, a user simply provides two tasks, one for training and the other for validations, right? And then just to create an instance of the policy that he or she wants to run, and then create a policy, a solver, which is the neuroevolution algorithm. In this notebook, which we provide a PGP algorithm, but there are a lot of other algorithms as well. And then you simply plug all this stuff into this sim manager, and then run this loop. So this is all you. If you want to write this loop, this is all you need to do. But apparently, EvoJAX wrap this all in a trainer. So this entire process will be transparent to the users. What the users need to provide is this algorithm, to specify this algorithm that he or she wants to use to create his or her own, policies and the tasks, and that's all. So this will allow the EvoJAX to train the policies smoothly, and within a short time, you will get some decent feedbacks. Okay, so this is the first demo, or say code that I want to illustrate. The next thing is probably more interesting. Let me show here. So the next demo that I want to show, I'm actually going to run this demo, is say abstract painting. So in the previous slides, I showed an example of painting a concrete image. Say, given an image of a Mona Lisa, train an agent to paint with only triangles, say 50 triangles, to arrange this triangle such that the resulted image resembles the given image. So that was the previous demo. In this demo, we are using the clip model, where the agent will try to fit a concept. For example, in here, if I say the prompt is Great Wave Kanagawa, then the agent will, through learning, say learn to paint this kind of images. So eventually, it's going to give you this kind of abstract painting that resembles the famous painting in Japan. That's the wave of the Kanagawa. Notice that the resemblance between these paintings, they both have this mountain Fuji here, and you can see here this kind of resembles a wave here, right? So that's what EvoJAX is capable of doing. It could. So this thing, what we want to demonstrate in this notebook is that EvoJAX is a modularized library. So although I said there are 3 components that the users could use, users are not required to use all of them. Actually, you could extract any one of them and use them as a standalone part. For this demo, we used only the neuroevolution optimization part, and used that part to train a network. The code itself runs on TPUs and GPUs, and it could scale really well. For example, if you have 8 GPUs, then probably you run twice as fast as you run on 4 GPUs, and same applies for TPUs. What I want to mention is that this work was previously implemented by Intel, my colleague, and before EvoJAX, the setup requires both CPUs, decent CPUs, and GPUs. But after we adopted EvoJAX, so this notebook can actually run on a single Colab. So you can see the complexity of the hardware is actually simplified, thus making this demo more accessible to a broader range of audiences. Okay, I promised you to run this demo, so let's try a different idea, for example. I'm going to go to this page, for example. Let's try, instead of Great Wave, let's try, say, I don't know, maybe Brain, for example. Okay, it's training. Okay. Yeah, right now, at first, you can see those triangles are really randomly placed there. It doesn't form any like a meaningful picture, but after a while, you are going to see some patterns. And while it's training, I want to show you the GPU usage here. Yeah, so you see, EvoJAX fully utilizes all the GPUs to reside on the machine. So we see really high throughput when we train with EvoJAX here. And as you can see here, yeah, I don't know about you, but I guess this is supposed to be a brain that EvoJAX is trying to evolve here. Yeah, so right now, as you can see, each 50 iterations takes about 10, 13 seconds. So this task I'm currently running on 4 NV100 GPUs. So with more GPUs, this experiment will finish sooner in a relatively shorter time. Yeah, we'll just let it run. Yeah.
I just wanted to comment that this also feels like it's running faster than Clip plus VQGAN. Although, like, I've not tried it on a 4V100 system, but it looks like it's running faster than that.
Sorry, it's running faster than.
Have you seen the Clip VQGAN collab that has been out there, which is somewhat similar?
Okay. Yeah, sorry, I haven't played with that notebook. Yeah. What we are trying to say is that so Intel really put great effort into this implementation. So we made sure that this notebook or the EvoJAX could fully utilize all the hardware resources that the user is providing and try to give results as soon as possible.
Just like A question. You're running on this collab, but you're telling it to run on your local machine, or
Yeah, I'm running it on my GCP machine. The reason is that for default Colab users, which I am, you will only get a K400, K40, or maybe K80, right? So I want to demonstrate that we could scale really good on like a multiple GPU. So that's why I connected to a local GCP machine.
okay, yeah, just to clarify because
Yeah,
you
just
you never get more than one GPU
but
on on.
you could run on TPU as well, because by default you get 8 core TPUs. So this code runs on TPU as well, just for the record.
Yeah, it would be okay. Okay, yeah, it would be really cool. Does it run on the TPUs like V2, like the ones you get on free collab?
Yeah. What I meant is code like a free collab. You could run the same code on free collab as well.
Mm.
No problem.
Okay, yeah, it would be
Yeah, I just forgot that because the Brax example was running on TPU, right? So I try a different hardware accelerator in this example, right?
okay.
Yeah,
Awesome.
yeah.
When it's running on, because you showed you had like four GPUs or
Yeah,
something
yeah,
like that.
yeah. Like if I go to the top of the notebook, you can see I'm currently running on 4 GPUs.
W- Like when you're distributing it, like you use, for example, a PMAP, right, or something
Yeah,
like
yeah,
that,
yeah. We're using PMap. Yeah,
and you just divide it in four.
yeah. We divided by the batch size by 4, and then distributed to the devices.
And then within each device, because I'm thinking, or I don't know if this is true. Like, okay, maybe within each device you can also divide it into whatever. Let's say 10.
Why do you want to divide it further into a single device? I'm not sure I
No,
understand.
I'm just thinking of ideas. The is it computationally because, for example, if you have a super like big model,
Yeah,
well, I mean, usually that fits your each of your devices like really quick. But I don't know, I don't know if this is a like different type of neuroevolution, but sometimes these evolutionary algorithms are each model is rather small, or I don't know if these models are bigger. So I was thinking, okay, if each model is small, then maybe you could subdivide it within each device to get like whatever speed up. I don't know.
yeah.
Like,
The thing is that yeah, you're right. Like for especially for like a deep learning task, because we have this clip model here, right? Some models could be large.
okay.
It could consume a lot of the memory spaces. But the point is that we could quickly distribute all the workload evenly. In this example, for example, evenly to all the hardware devices available on the platform. And so I mean that's kind of the best you can do, right? With all the
Mm.
hardware. That's the efficient way of using all the hardware accelerators.
Okay, had a related question
Sure.
because maybe I'm thinking so most of the intuitions I have about neuroevolution they come from NEAT, from the NEAT algorithm, which
Yeah, Nick is one of yeah, right.
uh, but that algorithm, I don't know if it's maybe too dynamic for the kind of stuff that maybe you're doing here, because I see a lot of ES strategies, which I guess are a bit different than NEAT. Can you clarify like what kind of algorithms you're running on this neuroevolution? Because I remember
Yeah.
NEAT build like a dynamic graph of
Yeah,
operations.
sure. Right. I actually have one slide, so later on to explain all
Okay.
the to demonstrate all the available supported algorithms currently in EvoJAX. But to give you a slight telling here. So yeah, you're right. what we are implementing right now are majorly like genetic algorithms or say evolution strategies, but there are a lot of other more, right? Like NEAT being one of them, right? It is possible to implement the NEAT and integrate that into EvoJAX, no problem, as long as the interfaces that we designed is implemented. Then it could be inserted and run smoothly on this entire on this entire platform. So that's the major message that we want to send to the users.
Oh, well, then I'll wait till we get to that slide. I'm very curious about that.
Yeah, cool. Yeah, thanks for the question. Yeah, okay. So yeah, it's currently training, but you can see this is almost brain like stuff, right? So yeah, feel free to play with the notebook and try your own ideas. So here's some like a funny story about this idea. We actually, so before release of EvoJAX, Intel and I actually tried to design a logo for EvoJAX using EvoJAX. So we tried like a various of keywords like neuroevolution and maybe some like science and math there. So we got some interesting images there. But we have different preferences, so we never settled to one single image that could represent the icon of EvoJAX. Yeah, but that's just another like interesting story that I want to share with you. So that's kind of a cool usage for EvoJAX, especially this ES clip demo, right? To design some logos using evolution strategies. Okay, I want to get back to the slides here. Yeah, so what I presented previously is the first two demos. Another one that I want to highlight is this multi-agent training is possible in EvoJAX. So what I mean by multi-agent training is that, so this is the world example that I showed you earlier. But right now, this is a modified version where, say, we spawn the entire population into the same environment. And these agents can see each other. So that means there are interactions between these agents. So what we find is that with this kind of a design, so first of all, it's apparently possible to train multiple agents in a single environment, in a single rollout. The benefit of this scheme is that because the agents could see each other, so the environment has a certain richness brought by these interactions between agents. And this kind of richness, environmental richness, is way beyond human design. This is good for especially reinforcement learning because that, say, we all know that the amount of data matters a lot for supervised learning, right? The equivalent of data is the task's richness. So with more richful tasks, the agent you trained could be better, say either more skillful, say, behaviors or maybe robustness demonstrated by the agent. So this kind of a multi-agent training presented by EvoJAX is what could possibly bring better performance for future like reinforcement learning practitioners. Yeah, okay. Yeah, so these are the demos that I want to highlight in EvoJAX. Okay, in the next three slides, I want to talk about user extensions. So that's also the question that Christian previously had, right? So the first component that I want to describe is the algorithm component. So as I said, we got three major components. The algorithm is the first part. So we have carefully designed an interface in EvoJAX where you simply need to implement this ME algorithm interface, which has got two methods, the ask method and the tell method. And these methods are already familiar for most of the neuroevolution practitioners, I think, where the ask method simply asks the neuroevolution algorithm for a collection of candidate solutions to be evaluated. And the tell method simply reports back the fitness scores of each of the populations so that the neuroevolution algorithm could update its internal state for the next generation. So as I said, the user simply has to implement these two methods, and then his or her algorithm will be ready to run in EvoJAX. So as I said, we've already received a lot of PRs from external contributors, EvoJAX being one of them. So in this table, what I'm demonstrating is the currently supported algorithms in EvoJAX. For each of the algorithm, we provide a benchmark for all the tasks, and you can actually see the scores, how each algorithm is performing. So this information, we hope that this information could provide some useful insights to the users when he or she wants to select the appropriate algorithm to run for his or her tasks, right? So that's what I want to show you here. I want to give you a walkthrough of the extension of the code quickly. Let me just pick one really simple example. For example, this CMA wrapper. So in this CMA wrapper, we simply wrapped an existing implementation which runs on CPU, but we demonstrate that's also possible to run in EvoJAX. It's just that the performance may not be as good in terms of speed, right? So as you can see, so first this code has only maybe less than 100 lines, right? So what I meant is that a user extension is simple in terms that, for example, if he or she already has some implementations of a certain algorithm and want to integrate quickly into EvoJAX to test its performance, for example, just to test the performance, then what he or she can do is just to make a wrapper, right? Create an instance in the instantiation method, then simply called ask and tell methods in the corresponding method, which I believe is widely available in the majority of the algorithms. So that's all the user needs to do, right? So as long as these interfaces are implemented, the algorithm could be run smoothly in EvoJAX. So it's just that simple. Okay, back to the slide. Okay, the next thing that is also the major focus of EvoJAX is that so we try to provide a lot of the examples in EvoJAX to try to demonstrate the capability of this software toolkit. For example, in the first release, we provided the 6 tasks, say MNIST and sequence to sequence. So these 2 tasks fall into the supervised learning domain. We want to demonstrate that EvoJAX could train, supervise, and learn the tasks also quickly. For example, MNIST could be trained on a single GPU within 5 minutes and reach a test accuracy above 98%. Which was not possible for a conventional implementation that utilizes only, say, CPUs. And for sequence to sequence, that's a demo provided by Flex, which in this task, the agent will receive a sequence, say this kind of simple math, right? 1, 2, 3 plus 4, 5, 6, for example. And the agent is supposed to give out the correct answer, also in terms of like a string or say an embedding space. So in this task, we purposefully composed a relatively large network. It contains, I guess, hundreds of thousands of weights. We want to demonstrate that EvoJAX is capable of training a moderately large network instead of only focusing on small networks. So these are the purpose of these 2 tasks. Then in the next set, we trained on cart pole, swing, and this robotic control task majorly with BRAX to demonstrate the speed up, right? We could train these tasks really fast, usually 10 or 20 times speed up. Then we demonstrated 2 novel tasks, the word-to-world and the abstract painting that I just demonstrated. The last example is created by our intern, Mayu Ogishi, recently, where she created this flocking simulation system. So what you are seeing here, so this is the environment. What you are seeing here, so these blue buoys represent fishes in a pond, for example. And each fish could observe the nearest 5 fishes around itself. Then it is required to they all move in constant speed, but they could select the orientation to move into the next time step. So the goal is everybody try to speed out a coherent action such that the entire flocking could move in more like a coherent fashion, what we observe in the nature. So we defined several reward functions in the task, and then we train an MLP to simply simulate the behaviors of these agents. And as you can see here, we kind of reached our goal, right? Each agent is moving in a smooth fashion, in a coherent fashion here. And yeah, so this is for task integration. Again, all the users need to do is to implement this, say, vectorized task interface, which have this step and the reset interface, which is quite similar to OpenAI's Gym environment, right? You simply implement these two environments, two functions, and you're ready to go. And as I mentioned earlier in this talk, although this is a vectorized task, the users does not have to remind him or herself that this is a vectorized task, so I have to keep the batch dimension in mind. Instead, you just write it as a single task and then later wrap it with the Vmap function. Then that's all you need to do. The JAX will just make auto vectorization of the entire task. And lastly, what I want to show you is the policy. So that's another component, a major component on EvoJAX, right? So for policy, it's the neural network part that the user could compose. For policy, the major function that a user wants to implement is this get action function. So the get action function, unlike in say traditional policies, it receives the states, and also besides that, it will also going to receive the parameters for the policies, because for EvoJAX, we have a global policy, one instance of policy. And instead, it accepts batches of data, one batch being the states, the observations, the other being the parameters. Then they are matched one by one, so that the global policy could generate different behaviors for different, say, individuals in the population. And that's how we eliminated this, say, separated policies in each process problem. Right now, in EvoJAX, we have implementations of 4 kinds of policies. The feed-forward network, which is simply MLPs, and the convolution net, that's what we used for MNIST classification, and recurrent networks, including a sequence-to-sequence model. And finally, we have this permutation invariant MLP, which just want to demonstrate a more complicated policy is also possible within EvoJAX. Yeah, so yeah, I think that's all I want to cover in this talk.
I had a question.
Yeah, sure.
Um, well, so first I get that okay, EvoJAX is kind of like more like okay, we're gonna define these interfaces that play well within each other, and I guess the trainer puts them all together, right? So
Yeah,
if some folks wanna concentrate on creating new tasks, then they can do that. Then I guess EvoJAX. But what the previous question asked would be more on the well, I guess on the ask and tell interface. Which what was that one called? Like the I'm guessing the algorithm. So so there's a task. There's the I guess the environment, and what was the other
yeah.
interface?
We have we have a algorithm interface, we have a policy interface, and then we have
Policy.
task interfaces.
Okay, um, in for example in the policy one, that's where for example you would code something with flags or something like that
Yeah,
to
in the policy. Yeah, let me just give you a quick example. Yeah, so these are the policies we currently have. So we have simplified task. For example, this MLP, where we use Flex to compose network, although this is not necessary, but I think that's a great library, so we use that one. Like as you can see here, so this is the policy itself, right? We simply compose it. You can do that with other framework as well. Then what we do is simply like get the parameters there, right? So simply initialize this entire policy network, get kind of the placeholders for the parameters, then try to initialize them so that later on we could use these placeholders to feed in the real parameters to get the actions.
okay, this is really cool. So like I could use, let's say, a task, an environment, but then code my own policy, and then if they follow the interface, then everything should like work.
Yeah. Right. So what I'm showing NLP is a relatively simple policy, right? So you can do all the crazy stuff. For example, this is what I mentioned. That we have this um, permutation invariant policy that's from our earlier paper. So you can see the policy is kind of complex compared with the previous one, right?
Mm,
I guess it's this part. So it's relatively longer. It contains all the like Alice TMs here and some attention mechanisms here as well. But as long as the interfaces are implemented, the whole complexity is hidden away. Users don't have to worry about that, and AppleJAX can simply run the entire and the code interface to run the policies smoothly and train the entire stuff and integrate the entire stuff into the training pipeline.
mm. I see. So and then I guess the training algorithm, like for example, evolution strategies, that would be, I mean, it would be the other interface.
Yeah,
Okay, this is really cool. So I don't know. This is more general because I don't know. I think most of us don't work with evolution strategies daily. Can you tell a bit about more like this versus like regular reinforcement learning? Like what's kind of the difference between like the evolution strategies versus like gradient based methods? I guess it's kind of what I'm asking.
yeah, I see. So OpenAI earlier published a paper, right? It says that evolution strategy is an alternative to reinforcement learning, right? So that's kind of the position there. So evolution, like to solve this kind of reinforcement tasks, like using PPO or say other gradient-based RL algorithm is one way, but ES is the other, or say neuroevolution algorithm is the other way, right? Actually, in some tasks, for example, traditional Atari games, neuroevolution algorithm has actually give better performances than other traditional IL algorithms, right? So that's kind of a promising. Another difference is that what I mentioned earlier in the talk, so most of the algorithms rely on differentiability, at least for the policy networks. But for neuroevolution algorithm, we don't have such constraints. We don't rely on the differentiability of the networks, right? So this gives you all the freedom in exploring some crazy architectures, right? As I mentioned, you could try to patch the entire screen and then try to pick out the most important patches instead of using the entire screen. Being one example, right? So this kind of the advantages brought by neuroevolution algorithms. Yeah.
Mm.
And one more difference, it's not a difference that what I want to mention is that for one interesting stuff, like a major contribution from RL is that they provided this value-based method, right, where you learn a value network to estimate how good or bad the current situation is, right, by collecting data, say from a random policy or say a behavior policy to sample data, then run a learn a value network on top of this buffered data, right? So this was possible because all of this run on say a standalone machine. So this data collection is like it resembles the supervised learning work which we usually see, right? This is difficult to implement in conventional neural evolution frameworks because all the processes are distributed on different machines, and you when you collect the experience, you have to transform back into a centralized location to learn this value network. It's doable, but it's apparently tedious, right? But right now with AppleJAX, because everything runs on a standalone machine, so we could do that as well, right? We have all the data collected on a single machine, so it's possible to learn a value network on this machine and use that value network to evaluate how good or bad the current situation is and provide training signals for the neuroevolution algorithms as well. So that's another advantage if you are using EvoJAX now.
Mm. When you say with EvoJAX you have it on a single machine, uh, like what does that mean exactly?
I mean,
Like,
a single processor. Sorry. So you previously have to spawn different processes or different threads, right, to do evaluations. So each process or thread are going to collect its own, say, data, observation data, right? You have to somehow collect them and buffer them into the same replay buffer for a value network to run, right, to learn. So
Mm.
this data collection is kind of a sort of tedious. What I mean right now is that with EvoJAX, because we run in a single thread, right? You run data collection. It's just from a vectorized task. So naturally, it's easy to store these experiences, right? Then you apply the same process. You run the value network on top of this play buffer. So that's kind of easier for the practitioners.
Okay,
Yeah.
I see. I have a question. I remember I don't read a lot of reinforcement learning, but I read the original ES strategies paper,
Okay.
which was a long time ago, I guess. And I remember they said like, okay, like you can beat RL, but you need like a cluster like with 1,000 CPUs.
Right.
So
So
it was okay. We're like you can beat it, but you have to scale massively. I remember that was kind of the idea. Um, so here, like with EvoJAX, we're in the same like regime. Like you still need like a lot of, let's say, compute, or I don't know, because here we would be talking about probably TPUs or something like that. But the idea is still to have a large number of uh, let's say agents to eventually beat RL in speed, or has there been other breakthroughs that make it such that you don't need a lot of hardware?
the thing is that like in terms of hardware, amount of hardware, so we probably don't need CPUs, but we need GPUs, so or TPUs, right? That's not gonna change. You want something, you gotta have the
Mm,
appropriate hardware. What's changing is that for CPUs, you have to maintain clusters. For example, most of my previous experiments run on Kubernetes, so that's clusters orchestrates, right? So running experiments on that is fast, but you have to spawn a lot of the machines, and to maintain this cluster is non-trivial. And probably machine learning practitioners don't want to maintain those clusters, so we want to kind of avoid that, right? So for some tasks, maybe you need not only CPUs, but also you need maybe for some parts. For example, if the task relies on a deep model, then you also need to use GPUs for the task itself, right? So
mm,
this kind of a mixture between of hardware, so add one more layer of complexity for setups. Whereas in EvoJAX, so you can run all of this on GPUs. So that's all right. You don't set up clusters. You don't set up different CPUs, GPUs. So I suggest that this makes life much easier for machine learning practitioners.
okay, yeah, that makes sense. So the idea is to use Jack's, let's call it native distribution, which is not distribution in different sense. Like you're relying on TPUs, for example, which are kind of like, I don't know. In the biggest case, I guess you could get a pod which has what, like more than 128 devices, and then you're going to distribute it in this. How do we call it? It's kind of a cluster, but it's not. Um, it's not distributed in the sense that you have to do the I/O yourself or something like that. But Jax just does it like for you natively.
Right.
So
Nowadays, like having access to multiple GPUs is kind of common, right? In most of the labs, because
mm,
this popularity of deep learning, people are already using multiple GPUs to training a single tasks. So I would say this kind of setting is common for machine learning practitioner, whereas a cluster of CPUs is probably not so common, right?
mm,
So
yeah. A related question: have you checked maybe Jax? Like I think Jax is trying to run also multi-host. This is kind of something I've seen around in the Jax forum, and there's also this. open how is it called? MPI
Yeah,
for
MPI, right.
JAX.
Right.
Have you checked all these other ways of trying to create like JAX clusters?
No, I haven't. But with that being said, I think that's a plus, right? So what they are trying to do is scaling up, which is a plus for EvoJAX, right? We don't with that. So EvoJAX could further scale up, run on multiple hosts, right?
Mm.
And I hope that, as you said, that this kind of complexity could be transparent to the end users, such that we still run the same code, but the world suddenly get better once we have more machines, right?
Yeah, it would be really cool because then I don't know if somebody, I don't know, your DevOps friend spawns a Kubernetes cluster with 1,000 hosts, then you can maybe try to use this multi-host and then well same code, right? That would be really really cool. I don't know how evolved that is, honestly, but it's something like very interesting. Like I don't know if you've tried to go that way with EvoJAX and see if it works.
I haven't done so, but as I said, so the major motivation, one of the major motivations is to make things fast, right?
Mm,
So as I said, for previous paper publications or the experiments I ran, I exclusively used the Kubernetes, and we released the code, but we've got feedback from end users to say this is kind of slow because most of the users don't have access to clusters. They have to rely on moderately sized like a server by with maybe 48 or say 96 CPUs. Although you have a lot of CPUs, but it's still running slow. So
mm,
that's what we hope that EvoJAX could help them, get a faster idea iterations and to replicate the results really faster. That's kind of what we want to do.
okay, awesome. As a user, I saw there's this trainer object. Uh, as a user, you can tell. I don't know what's the interface because JAX has like a lot of ways of running. Like you have JIT, you have PMAP, you have PJIT, you have XMAP. Can you tell EvoJAX like run the computation in a certain way that maybe the user knows exploits better the hardware?
Yeah, so that's kind of like a question about the design philosophy, right? So right now, our design philosophy is to hide this complexity from the users. So the users, what user want to care, will be interested in probably is just the algorithm, the policy, and the task itself, the train itself, like how the devices, how each of the operations put on each devices. You don't have to care about it. You just write the policy, then
Mm,
everything will run for you, right? So that's what we are targeting for. But what you said is probably for more advanced users where he or she wants a higher level control, more detailed control, right? So
mm,
so so but that's doable, right? As I described, the EvoJAX is designed to be modularized. So you can use any component as a standalone component, then write the rest of them, the task, for example, to distribute the task to different devices by your own, right? So nothing's stopping you from doing that. So that's also doable. But
mm.
right now in EvoJAX, we probably are going to hide this complexity from the end users.
I see. So I'm guessing. Okay, you control the loop. You control like the training loop, and you say, okay, if it has only one device, then JIT. If it has more than one device, then you
PMAP, yeah.
switch to PMAP and that kind of stuff.
Right, right.
And if well, I don't know. I don't know if you've thought about this, but for example, uh, I'm guessing. Okay, let's say eventually PGIT is optimal. Like, is there kind of a like I don't know if you're thinking about this like a way for the user to somehow specify this, but I think it's very tricky. But I don't know if you've thought about how the user can try to specify this kind of.
Yeah, I see. Yeah, yeah. That's a good question. So as I said, we have just released EvoJAX for maybe a little
Mm,
bit around 1 month, I think. We are getting user feedbacks. So right now, we haven't seen such like requests now. But sure, in the future, if we see such requests, we'll consider adding features like giving users detailed controls, as you said, and maybe adding more advanced JAX functionalities to allow further, control of different details for the end users.
okay, well, that's so right now it's okay. It's really nice. It's kind of a plug and play.
Yeah, that's what we are designing this kind of yeah, that's our design philosophy right now.
Mm, okay, that's really cool. If w- I have a question regarding like some of the demos. So the environments you provide, they have this render function, like kind of like Gym.
Yeah, let me just give you a quick example. For example, the card poll, for example. So for each render, although this is not required, but the user can implement a render function, right? So for
Mm,
this render function, it's going to get the state. State is the kind of observation from this vectorized environment. And the user can specify a certain index of the task. Say, I want to see this environment, for example. Then this function will just plot the state for this task instead of the entire stack, right? So the user is responsible for implementing this. Apparently, because we don't know what the task is going to be, so there is no way for us to implement this for the users. Right now, we are just using this pillow, use just the image draws. So we could plot say whatever we want in this environment, and
mm.
users may have different needs. So it's possible to also say do some crazy stuff in this render function.
Okay, that's really cool. But this runs on the host, right? Because Peel is
Run,
not in JAX.
yeah, it runs on the CPU. So the render function is mainly for like a visual confirmation of the learned policy. So although
Mm.
you see the scores is rising, but you don't know whether the policy is really learning stuff or has it discovered as kind of a like cheating stuff, right? Cheating maneuvers.
Okay, that's really cool. And so this is more like a user question, like if people say want to try to integrate something like that is not yet in JAX, like OpenAI Gym, I don't know, the lunar lander. Is it currently
Yeah, yeah.
possible to do this kind of stuff? Like,
In the current release, it's not possible. So as I mentioned earlier, the current training loop we use the scan function from
mm,
JAX. Well,
mm,
in the next release, actually, we are developing it right now. We are using the traditional for loop. In that way, even not JIT function. I mean functions that's not JIT compiled could
mm.
also be integrated into the for loop. Then in that release, it will be possible to run conventional tasks. But again, there will probably going to be a trade-off in terms of performance speed.
Yeah, and also I guess there would be like a limitation for, because then you you can only run the environment in a single device. Is this correct? If it's
Uh,
not,
that's not true. So, say for example, you could use uh, for example, the vectorized environment wrapper from the baselines, I think, from the baselines toolkit, and then you simply wrap, for example, the OpenAI Gym environments. Then this environment, because it is a wrapper, right? It will provide it will provide the vectorized observations. Then after that, you simply convert it into a JAX tensor. Then it can plug into AppleJAX. So that's how
mm,
it will work. Did I
for,
make
for,
myself?
from the implementation side, like, because JAX is very restrictive in a lot of ways. How do you like tell JAX to, hey, this is not JAX, but put it in
No, no, no.
different.
You don't have to do that. To say say you have this say vectorized environment wrapper, right? So
Mm.
you wrap this wrapper around a bunch of tasks, OpenAI gym tasks, for example. Then the output, the observations will be a batch, a tensor with batch sizes, right? So probably it's in NumPy, right? NumPy for format. It's a NumPy tensor. Then you
Yeah.
essentially convert it into JAX tensor, right? Into JAX. So that's just one function, one call, right? Then
Ah,
you
okay, I see.
tensor to
So,
EvoJAX. That's all, right?
okay, so it's kind of vectorized, but it runs on the host.
Yeah, it runs on the CPUs. Yeah, I would say.
Ah, okay, okay. I don't know have I don't know if well, it depends how you're gonna run it. But have you checked these functions from Jax called I don't know ID tap or what's the package? Um, it's I forgot the package name. It's in experimental and it lets you the call host callbacks. Have you checked that functionality?
No, haven't.
Ah, okay. I've only used it for debugging, but it lets you run like Python code. Uh, well, on on the devices. I guess it's what it's trying to do. I only use it for printing, but
Okay,
I don't
okay.
know if you could try to like run the environment on each device also. I don't know how that. I think that doesn't make sense
Oh,
for GPUs, but maybe
yes,
for
I see
TPUs.
what, yeah, I see what you mean. So yeah, it's possible to insert a callback into this like a JIT functions such that this part will be like treated specially, right? From
Yeah.
what I know is that yes, you can insert like printing or other stuff in that, but if you want to convert a JAX tensor, say you got a three segments of code, right? So the front one will just run some computation, then it's your host callback, then you get back to the JAX domain, right? So if you
Mm,
generate some tensors in segment number one, and you want to, in the say callback to convert this JAX tensor into something else, then probably that's not doable if I'm correct. So there's going to be some data transfer limitations. So you can do
mm.
something if that's not related to any tensors from segment one, it's okay. But if that's the case, then probably you are going to run into some difficulties there.
Yeah, yeah. It's not fast. I don't know. I'm not sure about this. Would love to ask Google, the people who design XLA or JAX itself, like if this host callback, because I understand that TPU V3, they each device actually has like a host. That's what I understood from the V3 TPU V3 architecture. So it made me think, okay, if each device also has a host, like a VM, then can it also run like some Python code there?
Um,
Was my question. And then okay, if it can actually, if each device can run some Python code, then it would be very interesting if the device, the host callback could actually, for example, in this case, run the environment.
yeah, that would be really cool. Yeah. So, but yeah, so I know that I'm not familiar with TPUs, like all the usages of TPUs, and also like Jax team is really is amazing, right? They're working on these new features almost every day. So what I said could be wrong previously said, right? So this host back stuff. So I'm sure that one day they are accepting user requests, they are trying to fulfill user requests constantly. So I'm sure one day what we want to do could be implemented in JAX. So
Mm.
yeah,
Okay, yeah, it'd be really cool. I don't know. I'm saying this because I once got in a discussion on the JAX forum of how to try to load data into each device. Uh, like imagine like I don't know, like a PyTorch data loader, but distributed.
yeah.
and then like people were giving ideas, and one idea was, hey, why don't you use this device like callback? So and the thing, I think it's very similar to what you're saying. Like the question was, okay, I want to scan over like the training,
Yeah,
but I cannot scan the data generating process, which in this case is kind of the environment.
yeah, yeah, yeah.
And
Sounds
then I don't know, like somebody from the Jax team suggested, hey, use this. And I tried it, it actually works,
okay. Cool.
but it was very slow.
Yeah, it's yeah, but you know, as I said, so Jax is advancing every day, right? So maybe later they will release a feature that will allow this to happen and run fast, right? So right now, like for EvoJAX, our short-term solution is to support both the scan and the traditional for loop. For JAX-based tasks, the users can rely on the scan function, whereas for
Mm,
conventional tasks, the user could choose to fall back to the traditional for loop. Besides some performance fallbacks in terms of speed, it should be trainable. As I mentioned previously, we are testing, say, Isaac Gym as well. Isaac Gym is accelerated by GPU, but also it's not JAX. But with for
mm.
loop, it's also possible to train Isaac's environments or say tasks in Isaac Gym.
Okay, yeah, that makes a lot of sense. I think the for loop is
Yeah,
not that slow.
yeah,
If each step is sufficiently, like, I guess, big, or
yeah. It's not that slow. It depends on I think it depends on how you write the training loop inside that for loop, right? So if you properly JIT everything and make sure that everything is on GPU, the performance like a difference is not that obvious.
mm, yeah, yeah. A scan is ideal, right? It's kind of the,
Yeah,
well,
the
everything is
yeah,
Jax,
yeah, yeah. It's a unit operation. Yeah.
but yeah, what I kind of got the sense is, okay, if your step is sufficiently big, like it's okay to use like the for loop. And yes, especially if you want to interact with something, because the host callback again was not that fast. um I had like a, okay, no, I had a question but I forgot. Sorry.
No problem. Yeah. So
Um,
yeah, so as I said, we encourage users to extend AppleJAX and run our experiments. And if you have any questions, you can just send emails to us. So we have put our email address in the GitHub page. So feel free to ping us or say send us open an issue there or send us emails. We welcome all the user feedbacks, and we are open to any user suggestions. What Christian mentioned, we will consider release high level control. I mean detailed level control if that's what the majority of the user requires.
awesome. I'll wrap up in that case. And sorry we went overtime. Thanks for staying on, Eugene, and thank you, Christian, for the great questions. I'll thank the audience as well for joining. And again, I'll update if you're watching the recording. There'll be the link to EvoJAX repository in the description. Click on that and reach out to the authors and creators if you have any questions. I'm sure they're super active and will be happy to help you. So thank you so much again, Eugene and Christian.
Awesome. Oh, yeah. Thank you for having me.
Okay, thanks,
Thanks.
Hamlian.
Yeah. Okay.